All right, welcome to our live stream. My name is Chuck Ridgway. I'm the Automation Technology Manager here at Horner. And the reason we're doing these live streams is we're really trying to provide multiple opportunities for our customers as well as our sales channel partners to interact with us on a real-time basis while providing some content which hopefully you'll find informative. So as always, joining me today for Count Me In, our webinar, or really more of a live stream regarding connecting encoders to Horner OCS, is Casey Gardner. How's it going today, Casey?
Not too bad. How's it going, Chuck?
It's going pretty well. So you've helped lots of customers kind of wade their way through interfacing with encoders with our all-in-one controller products. Any advice for those who are looking to do that in one of their future applications?
Yeah, one of the best places to start is usually with our manuals, which you can find at our website. We'll post in the links down to the video. But a lot of the manuals actually go through each different mode and step, and even registers that are used for all the different types of configuration for high-speed counting. And I find them really helpful as a good place to start, at least, for sure.
Yeah, I mean, for a lot of things, our products are real easy to use, including really encoders. It's not that difficult either, but certainly in terms of needing reference information to really, fully integrate the, an encoder into a Horner all-in-one controller, starting from the manuals a really good idea. Great. Well, why don't we go ahead and get started? Just to remind you, Casey is going to be monitoring the comments, keeping an eye on questions. As you have any question, feel free to jump in at any time. You have the ability to chat those in, make comments, questions at any time. And, Casey will interrupt at the appropriate time and we'll get those questions answered. Again, this is an opportunity for you to, kind of steer the conversation a little bit even with some of your questions, as we try and provide you with some useful content. Okay, let's go ahead and get started. Very good. Okay, so count me in. Encoders, connecting encoders to Horner OCS. Okay. All right, let's go ahead and get rolling here. Okay, let's start off with just the basics. What is an encoder? Well, an encoder is a mechanical device that's typically used to convert motion into an electrical signal that can be read by some sort of control device. And in our case, that would be a Horner all-in-one controller. So remember, what we're known for are our operator control stations. Those are all-in-one controllers that combine the functionality of a PLC with an operator interface, with built-in I/O, all kinds of great networking capabilities, and really, interfacing with encoders is one of the things that we do pretty darn well. So getting back to an encoder, effectively this feedback signal that is provided by the encoder into a controller like ours can be used to determine position, count, speed, direction, a whole variety of things. Now, really, you can look at encoders in a couple different ways. You have the most common encoders, which are called incremental encoders. Now, they don't necessarily have any memory as to what their absolute location is at any given time. So on a power-up scenario with an incremental encoder, you almost certainly have to make some effort to establish the current position of the machine before you start operating the machine after a power-up. Whereas with absolute encoders, they're constructed such that regardless of the position of the shaft on the encoder, they'll know precisely where they're at, and it can sometimes make it a little bit easier in terms of powering up and getting going because the position of the machine is a little bit more known at power-up. Now, taking a look at incremental encoders in terms of the insides and how they work, first of all, before we go any further, I just want to give a shout out to the Encoder Products Company. It's a great company. They manufacture terrific encoders. We have a lot of mutual customers that use our products with their encoders. Now, that's not to say that our products can't be used with a whole variety of great manufacturers' encoders out there. But because of some of these great graphics that Encoder Products has created for kind of explaining how their encoders work, and we decided to use those today. And because they are a great company, I just wanted to give them a big shout out. Okay, so let's take a look at the inside of an encoder. So what you see there is that disk, and you can see that there are areas of the disk around the outside there, really a series of opaque lines. So as the shaft rotates, you are basically going to see that the LED, you have an LED on one side of the disk, is attempting to shine through those lines, and a photosensor on the other side is basically detecting the...
One sec. Sorry, I couldn't quite...
It looks like Siri is really interested in encoders today, so she decided to pipe in. How about that? But anyway...
I seem to be having trouble hearing you. Sorry about that.
So this is where we ask Siri not to disturb us. Let's get back to how encoders work. All right, I guess I'll learn my lesson and figure out how to turn off Siri before we start. Okay, so light's going to be attempting to pass through the slots in the disk. A photosensor detects the presence or absence of those lights. A sine wave type pattern is established from the photosensor, and then you have additional electronics that effectively takes that sine wave and creates a series of electrical pulses or a series of output pulses. And if you take another look here, you can see kind of how it all fits together. Okay, now let's look at those pulses in more detail. Okay, so encoders are typically specified in lines per revolution. You know, how many of those lines are around the disk for one revolution of the shaft, okay? Sometimes that's called cycles per revolution. So if you have, let's say, a typical number might be, say, 1,000 lines per revolution. Now, you've got actually two pulse outputs that are provided, the A pulse and the B pulse, okay, and those are out of phase. And if you take a look at the diagram there, you can see that for the A pulse and the B pulse, that you've actually got the leading edge of A and the leading edge of B, the trailing edge of A and the trailing edge of B. So just looking at those two pulses, you can actually have a count of 8 for two complete pulses. So for 1,000 lines of resolution, you actually can get up to 4,000 counts. So that's quadrature, if you will. Two signals out of phase that you can use to effectively quadruple your resolution. Now, often available with encoders is something called a marker output. Now, that's a third signal, often identified as Z, that is only on one pulse per revolution. And that basically marks mechanical home, if you will. And that signal is typically gated with either the A pulse or the B pulse. And if you look at that diagram there, you'll see that in this case, it's gated with A. Okay? So in an application that is rotary in nature, let's say you've got 360 degrees of total travel, and so therefore one revolution of the encoder represents a complete revolution of the machine. In that scenario, marker could be very useful for the purposes not only of kind of resetting your count potentially, but also in really helping you very accurately establish mechanical home. Now, for a linear type application where you are moving from, say, one location to the other, and to get from that location to the other, it's going to take many, many revolutions of the encoder. It's not quite as useful to have a marker. Okay, so we've taken a look at those pulses, what they look like. Now let's take a look at the electrical signals that are coming out of the encoder. Because if you can't electrically get a compatible signal between the encoder and the input of our all-in-one controller, then obviously you're not going to get the results you're after. Now, most encoder manufacturers have multiple options when it comes to the electrical output of the encoders, of their incremental encoders. For instance, a differential line driver is a very common output. So in that scenario, for every pulse, you're going to get effectively a complementary pair of signals. So for the A pulse, you're going to get an A and an A naught signal. For the B pulse, a B and a B naught signal. For the Z pulse, a Z and a Z naught signal. Now, in the case of our Horner OCS products, we're definitely compatible with differential line driver, provided that the voltage level is compatible with 24 volts. Most of our products require 24 volt level signals for the encoders. Now, we have some that can accept 5 volt signals, But today, at least in this industrial marketplace, it's really most common for PLCs and controllers like ourselves to really primarily support 24 volt levels. And that's true here. So if you've got a differential line driver output option with a 24 volt compatible voltage level, that will work really well. Another option that can work really well is something called push-pull. Once again, this is typically compatible with 24 volt level signals. Push-pull just kind of means that, or does mean, that it's compatible with both, that it provides both syncing and sourcing outputs, which means it's compatible with both syncing and sourcing inputs. And in the case of our Horner all-in-one controllers, syncing inputs or positive logic inputs are the most common by far. So a push-pull is another good option, again, provided that 24 volt levels are available. Now, sometimes push-pull is also kind of referred to as totem pole, but sometimes that has the implication, totem pole that is, of being 5 volts only. So if you do have an encoder that advertises a totem pole output, make sure that it's 24 volt compatible before you decide to integrate that with one of our products. And then lastly, another option is open collector. So with open collector and with encoders, this is almost always NPN open collector. With open collector, we are compatible with that signal, but it does require an external pull-up resistor in order for it to interface with our positive logic inputs. So if you have a choice in terms of the electrical output, don't choose open collector. If you've got a retrofit or something where you don't have a choice and you need to interface with open collector, that's okay. It just probably means there might be an external pull-up resistor required in the circuit. Okay, now let's take a look at a little more detail at some of the specific interfaces on our Horner all-in-one products. So what you see in front of you here is the micro series of controllers. And the micro series of controllers, just like the rest of our OCS products, which feature both built-in I/O and screens, have full compatibility with encoders. So in the case of the micro series, if you look at the terminal strip, you won't see any specific notation in terms of which inputs are high-speed capable. Now with our Horner controllers, we typically have somewhere in the neighborhood of 12 digital inputs on a typical built-in I/O option. Okay, and that's definitely true with the micro series. And 4 of the 12 almost always are high-speed capable. And in the case of the micro series, you need to take a look at the user's documentation to kind of identify which products, or which inputs I should say, are the ones which are high-speed capable. So what you see there on the screen, I've circled the 4 input 9 through 12, which is what you'll typically find in, say, an X4 or an X7. And I happen to have a, oops, wrong camera. There we go. I happen to have a X7 right here, so I'm just going to go ahead and show you those high-speed inputs. So our middle connector here is where our digital inputs are located, and we have I1 through I12. And in the case of the X7, which is what this is, as well as the X4 and the upcoming X10, it's these last 4 digital inputs, I9 through I12, which are the high-speed capable ones. So that's something to keep in mind, that depending on the product you're using, it may be a different point in the terminal strip where you need to connect your high-speed signals, including encoders. Okay, now let's turn our attention to the XL series. Now with the XL series, as many of you are probably familiar, instead of having just one primary I/O option, with the XL series, you've actually got several. So a Model 2 has 22 built-in I/O, a Model 6 has, I believe, around 30 I/O built in, and then the other models are more or less in between. But you've with all of those models, as long as there is built-in I/O, there's a Model 0 that has no built-in I/O, but as long as there's a built-in I/O, then you're guaranteed to have 4 high-speed inputs. And in the case of the XL series, those are always labeled with an H for high speed. So let's take a look here. Now the location of those signals is going to vary depending on model. This is a Model 2 that I've got here. That refers to the I/O option on the back of this 7-inch OCS. And you'll notice here right in the middle, you'll see an H1 signal. So that's the first high-speed input signal. This is a little bit of a goofy pinout. We'll be the first to admit that. But when you put a lot of I/O on a product, sometimes you got to sacrifice. So you'll actually find H1 on the other side, like I showed you, and then H2, 3, and 4 here on another connector. So while that's a little bit of a goofy pinout, it certainly doesn't hurt anything when it comes to the system performing flawlessly. So I just wanted to kind of point out where you can find those high-speed inputs. Okay. Now let's talk about the specific connections between the encoders and the high-speed inputs. So for really all of our modern products that support encoders, they actually support as many as 2 when you're talking about OCS products. So you could actually have 2 encoders connected to the 4 high-speed inputs if that was needed in your application. So as you can see here in this scenario, the A signal and the B signal are connected to H1 and H2 respectively. If you have a second encoder, you're going to connect those to 3 and 4. And then, of course, you still need to get the commons connected. Now, one thing you'll notice is that we don't connect the complementary signals of A0, B0, and Z0. So with our products, for the most part, you're really just connecting the primary signal of A, B, and Z if there is an encoder, or I'm sorry, if there's a marker. And then the next page shows that if you do need a marker, then you're going to be limited to 1 encoder because you're going to be taking up 3 of the high-speed inputs instead of the 4. So therefore, you don't have room for 2 full encoders. So in this case, you can see we're connecting the Z signal to H3. So this is the connections we would make then if we're talking about a single encoder with a marker signal. Okay, now there's more to do than just wire things up, however. We do need to configure things. And I'm going to show you in a minute or so how to do that in Cscape. So there's some things that we need to configure, some questions we need to ask ourselves as we head into the configuration process. Some things such as, what is the signal order? Now, everything I've shown you in diagrams has always been A leading B, and when A leading B, you're counting up, and when B is leading A, you're counting down. Okay, depending on the direction things are traveling, the shaft is traveling effectively. But not all encoders are manufactured that way, so that is something that has to be configured. Another question is this a linear or a rotary application? And the reason that can be important is very often it's important when you're thinking about what's going to cause the encoder to reset to 0. Okay, so if you've got a linear application, you're basically moving something from point A to point B, and that may be over many revolutions of the actual encoder itself. And so what's really going to be 0, if you will, is probably some sort of home switch or home location. Okay, so it's not likely going to be something in the encoder that you need to set to cause that to reset. It's going to be some sort of external signal. But in a rotary application where there's 360 degrees of total travel, you very well may use something like the marker pulse to reset to 0, or you might use the total number of possible counts in one revolution to reset the signal to 0. So those are some questions you have to answer as you head towards configuration. Okay, so let's dive into configuration. And here we go. All right, I'm firing up Cscape here. Okay, so let's get started. Let's start with one of our entry-level products. I'm going to go here under Hardware Configuration, and I'm going to go ahead and select a micro OCS product here. Let's go ahead and select an X7, although to be honest with you, the encoder configuration for an X4 or an X7 model in the micro series is going to be the same. Okay, but let's go ahead and select an X7, and then the high-speed counter configuration is included in the local I/O tab, and encoder configuration is really considered part of high-speed counting. So let's go to the local I/O tab, click under Config by the I/O, and then Module Setup. Now let's go ahead and select here digital in/high-speed counting, because that's really what we're doing with Quadrature, is we're doing effectively a variation on high-speed counting. Okay, so what you see here is we have a maximum of 4 counters. I'm going to go ahead and see what my options are here with number 1, and we see that it is Quadrature. Okay, so that's what I wanted to select here. You'll notice that number 2 gets grayed out because when we're using Quadrature, we're using 2 inputs. Now remember, my high-speed count input number 1 and my high-speed count input number 2 may actually be, and are in this case, the 9th and 10th pins on the terminal strip, but what we're really referring to here are the first 2 high-speed signals, okay, regardless of where they are on the terminal strip. Now, we've selected quadrature. Now we need to make sure that we have the signal arrangement proper. And in this case, this isn't what we want. If 1 leads 2, and we wire the A signal to 1 and the B signal to 2, then when 1 leads 2, we want to count up, not down. So let's change this to count up. Okay. All right. And then the last thing we can potentially configure is this counts per revolution. So if we've got a linear application where we're going to be moving again from one end to the other, and we're over many turns of the encoder, then we don't necessarily want to limit our counts per rev. We want to leave this at 0 so that regardless of how many revolutions as we head in a positive direction, our numbers are going to keep getting bigger. And then we turn around going the other directions, our numbers are going to keep getting smaller. So in this scenario with a linear application, we would leave this at 0. But let's say we had a rotary application and there were 360 degrees of total travel, and we wanted the encoder to automatically reset to 0 when we get to that maximum count. Okay, so in that scenario, let's say we had 1,000 lines on our encoder, which, to review, 1,000 lines equals 4,000 pulses per revolution. So in that scenario, we would probably want to set, especially if we're just going to use the number of pulses to reset to 0, we would make our counts per revolution configured to 4,000. That way, as we continually rotated, when we went past 4,000, we would effectively be going to 0 and starting back up again on the 0 part of the cycle, if you will. So that's one of the scenarios, a rotary type application where you would set the counts per revolution, whereas on a linear type application, you just leave it at 0. Now, if what you wanted instead was you wanted the marker to actually reset the counter, and you actually use a marker in the application, then we could actually go to input number 3 here, and we could configure this as the marker. And then we would have our options in terms of, okay, when this marker turns on, we see that marker pulse once per revolution, we're going to perform a reset. What kind of reset is that going to be? We give a whole lot of options. And this is one of those cases where Casey's advice of, hey, check the manual is a good one, because 90% of the time, the answer is you want to asynchronously reset the counter whenever you see the rising edge of that marker. But, there could be other scenarios as well. So checking out the user's manual would probably be a good idea. And of course, you're going to want to check out the documentation with your encoder as well to see how that's been configured. Okay, so again, this is another scenario where we've got one encoder connected. We're using a marker. If we're not using a marker, of course, we can just disable this input number 3. If it's an application where we have 2 quadratures we want to support, we can do that with the micro series as well. We can change and disable this marker, and we can make that instead. We can make that another quadrature. Again, we're probably going to have count up instead of count down. I really should talk to engineering about changing that default. And then away we go. So this is the micro series configuration. Now remember, we have a lot of products in addition to the micro series. So what I'm going to do next is I'm going to show you the configuration approach if you're using an XL series product. Effectively, I'll go back to hardware configuration, and instead of an X7, I'm going to go ahead and change over to the XL series, and I'm going to go ahead and select one of my favorite products once I find XL series here. There we go. I'm going to switch over to one of my favorite products, and that's the XL4. I have a soft spot in my heart for the XL4. I think it's a fantastic product, as many of our products are, if not all of them. But this is one of my favorites. So let's go into local I/O, hit the config I/O button, module setup, and high-speed counting. Okay, things look a lot different here. And really, though, they're not that different. One thing Casey wanted me to remind you of, with the XL series controllers, they have some really capable high-speed counting. But because of trying to squeeze some things in to to different modes into the limited memory space in our FPGAs and our programmable memory devices that are used for doing the or programmable logic devices that are used for doing high-speed counting. If you are looking to support more than 2 counters, then don't forget that we also offer a 4-counter mode, which does require a firmware change if you're interested in actually doing 4 counters in an XL series product, like an XL4 on up. Now, if you're just connecting an encoder, or maybe even 2 encoders, you don't necessarily have to use 4-counter mode. You can do that from the standard mode. But Casey asked me to remind you of that, and I thought it was a great idea. Okay, so the first thing you'll notice that's a little bit different is in the case of the micro series, we kind of have a fixed memory map in terms of one thing I haven't really showed you yet is the memory map for things like manual resets from internal I/O points and those sorts of things. And I'll be showing you those shortly. In the case of the micro series, all those internal memory points are all fixed. In the case of the XL series, you can move those around if you want. So that's what these are for. But I would say 98% of our customers are just going to leave these at the default. And then we also have a filtering setting here, which I'll come back to in a minute. But down here really is where we're talking about our high-speed counter configuration, including our quadrature. So for counter number 1, let's go ahead and configure that guy for quadrature. Okay. And you can see there's just a lot more programmability here. All right, so here we go. With 1 lagging 2, we count up. No, we don't want that either. We want, if 1 is leading 2, we count up, or if 1 is lagging 2, we count down. We probably should do a better job of making that terminology more consistent from product to product. Again, another suggestion for engineering, but as long as you pay attention, it's not a problem. Okay, so when 1 lags 2, we're going to count down. And in this case, the defaults for quadrature are the A signal will be connected to external high-speed counter signal 1, and the B will be connected to high-speed counter input 2. Okay, and that seems like a reasonable configuration. And then down here is where we configure whether there's a marker pulse or not. And for now, let's say there's not, because that's the most common case. Now, what are all these other functions? Well, in the case of the XL series, you have the capability of utilizing your high-speed input signals. And remember, you have a total of 4. You have the flexibility of using those for a whole variety of different things. You can use them for a reset signal. You can use them for a latch signal. You can use it for a preload to load in a specific value. There's a whole bunch of things you can do with that. And of course, you can use it for markers as well. So effectively, we give you the flexibility for each of these functions of the high-speed counter to decide if an external signal or whether maybe an internal I/O point are used for each of these functions. Now, in a typical quadrature type application, one of the things you're going to want to be able to do is you're going to want to be able to clear, okay, the high-speed, the accumulator effectively, the position. So as you power up, you're going to want to go to a known position, which may be 0, and then clear the counter. So in that scenario, you at least are going to want to configure an assigned I/O output, that's basically an internal bit, to perform the clear function for you. And it just makes logical sense that when that %Q bit goes high or on, that's when you're going to do your clear. Now, you may have another scenario where you don't necessarily want to go to 0 on power up every time. Maybe what you want to do is just go to a known position. So maybe you're sitting there at exactly 16,500 counts, or at least the equivalent of that. And at power up, you just want to plug that number in and just say, that's where I'm at. So in that scenario, you're going to want to do what's called a preload function. Okay, so again, let's go ahead and assign a specific I/O output point to the preload function. And again, just for logic's sake, when that's high or a 1, we're going to go ahead and do our preload. Okay, so that's a good typical configuration for a quadrature encoder. You've configured a preload, you've configured a clear. You're going to do that internally. That's a pretty good function. Now, it doesn't have to be done that way. You may have a scenario, even in a linear application, where you think it's more accurate, and you're probably right, to use let's say a photo eye or some sort of, Hall effect switch or something as home position. So in that scenario, instead of your clear being an assigned output point, it probably makes a lot of sense for that instead to be, or if you're really concerned about accuracy of home, you could make that one of the high-speed inputs as well. So in this scenario, if we've got a photo eye or some other switch that marks specifically where home is with a degree of accuracy, then we can assign that as the clear function. And then we have more choices besides high level. Probably what we're going to want in that scenario is we were going to want to do a clear on a rising edge. So if on the rising edge of hitting that photo eye, boom, that's when we want to do that clear function. So as you can see with the XL series, you've just got more flexibility in terms of how you configure the system and how you utilize your 4 high-speed inputs. All right, so I'm going to briefly break away from Cscape. We'll be back in a second because I want to talk about specifically where some of these internal I/O points are mapped. And I also want to talk, at least in theory, about this filtering value, but I'd want to do that with some graphics before we dive into the configuration part of that. Okay, so we've answered our questions here. We've gone through the first part of the configuration. Now, when it comes to operation time, we really need to be concerned with, okay, where are these encoder counts going to be showing up in our memory map inside of our controller? And as those of you who are familiar with Horner controllers know, AI, AQ, I, and Q are the different memory types for real-world I/O. And encoders come in real-world I/O, and they're controlled with real-world I/O. So you've got a fixed memory map in the case of the in the case of the micro series. We're talking micro series here. In the case of the micro series, you have a fixed memory map, and it's a pretty simple one. It all fits in one small chart. You can see that for the last column covers quadrature, okay? And so our accumulator, or the current count, if you will, from the encoder is going to be coming in analog inputs 5 and 6, okay, as a double integer value, okay? So those as a double integer value are going to be showing you the accumulator for the encoder, all right? If you've got 2 encoders connected, okay, you go down and you'll see that high-speed counter 3 is where the second quadrature accumulator is located, okay, and that's at AI 9 and 10. And then the bits that you would use to do a clear function or a preload function are shown in the lower right-hand corner of the chart there. That's Q17 through Q20, okay, for a clear and a set for the first quadrature, and then the clear and a set for the second quadrature. Okay, so that's the map, if you will, memory map for the micro series. But if we go into the XL series, I've just captured a really small portion of the memory map for the XL series. Now, it's still the basic concept is the same. Okay, you're still talking AIs, AQs, Is, and Qs for monitoring and controlling the high-speed counter function, including quadrature. It's still that last column there that has the quadrature information, but now you've got a whole lot more capabilities available to you, a whole lot more flexibility. But the basics are still there. The accumulator for the first quadrature, in this case, though, the default is AI 401. The preload value that we might want to load into an accumulator for a known position, you know, when we do a preload function, we're going to put that into AQ 401 through 402. That's the first part of that second section of that chart there. And then our digital output bits that we're going to use to perform a clear, perform a preload internally at least, those are shown in the bottom part of the chart. So getting back to Casey's suggestion, which is a great one, you know, this is a portion of the manual for the product you're using that you should absolutely have earmarked if you're going to be doing encoder type integration. It's not complicated, but you need this reference information. All right, now let's talk about the filtering option that I really didn't get a chance to go into yet, and I'll go back to that in Cscape. So what is the filtering option? Well, what we've got here on the screen is you can see a pulse train coming in on the top there. Okay, so that's our input signal at the top. All right, at the bottom, or in the middle, I guess technically, you see what looks like a sine wave there. Basically what that is that's a sample frequency. All right, so why do we need filtering for an encoder signal? Well, first of all, you might not. Okay, you very well might not need filtering. But if you've got an application where you have some spurious noise that is causing some extra pulses to occur that are maybe relatively tall in terms of magnitude, but are skinny in terms of their duration, and that's going to be typical for a noise type signal as opposed to your normal pulse type signal, then you're going to want to filter those out. And if you can't do it electrically very easily, then doing it through our built-in filtering is an option for the XL series. So normally the rule of thumb would be this. Let's say that you're dealing with a frequency of about 10K on the pulses coming out of the encoder. Now, of course, the frequency of the pulses is going to depend on two things, right? It's going to depend on the number of pulses per revolution and the number of revolutions per second. So you take those number of pulses per revolution times the number of pulses per second, times the number of revolutions per second, and that's going to give you the frequency coming out of your encoder. So let's say that we do that math and it's basically a maximum of, let's say, 10K. So we're never going to get more than a 10K pulse train coming out of our encoder. Well, then we're probably, as a rule of thumb, going to want to set up a sampling frequency or a filtering frequency that's about 4 times that. So let's say 40K. And then the other thing we configure, and that's where these little lines come in, if you can kind of look at these little lines, those little lines on the left there are basically looking at each sample. So you'll not only configure a frequency at which you want to sample, but you'll also configure how many consecutive ones are going to actually represent a valid pulse. In other words, I'm expecting a pulse of X width, and I'm going to sample it 4 times the frequency, and let's say if I don't get at least 4 consecutive ones in a row, then I'm going to assume that that's noise and not a valid pulse. Okay, so that's really what the filter configuration is all about. Configure a filtering frequency and configure a number of consecutive samples that have to agree to be a 1 before you actually count that as a count, if you will. Okay, and getting back to Seascape, okay, here is where, see if I can find my mouse, there we go. As we go in and configure this filtering, this is where I can configure that frequency, let's say to my example of 40,000 hertz. Oops, I probably have it too high. There we go. I set up the filter frequency and then the number of samples. Oops. And I'm having all kinds of trouble here. Let's just go ahead and type this in. All right. All right, so you configure your number of samples here and your frequency there. And then you're going to configure which of the inputs. Now remember, with the XL series, H1 through H4, as they're labeled on the terminal strip, always correlate to I9, I10, I11, and I12. So if it's the A and B signal that we want to filter, then we would, and they're wired up to the 9th and 10th terminal on the terminal strip, then we would check those boxes there. Okay, so we're going to set our frequency and we're going to set our number of consecutive samples if we need to do that. Now, in a lot of applications, I would say most applications, you're going to be controlling your spurious noise with good wiring practices, good wire routing, all those sorts of things. But in those rare instances where filtering is required for a quadrature type application, then this is something to be aware of. Okay. All right, so that is a look at incremental encoders and the basic process of selecting them, connecting them up to one of our all-in-one controllers, whether it's the micro series or the XL series, going into configuration, setting up the options properly, figuring out how you want to do your reset, whether you're going to do it from an internal I/O bit or whether you're going to do it from an external signal or a marker, getting all that configured, maybe adding filtering in those rare cases where that's your only option to clean up some spurious noise. So we've accomplished that. Now there's one more thing I want to cover as it relates to encoders, and that is absolute encoders, because all the discussions we've had for the most part has all been about incremental encoders. But there are absolute encoders, and we need to cover those as well, because they also have a lot of a lot of application in a variety of different applications. So in the case of a absolute encoder, they work a lot like incremental encoders do, except if you take a look there at the graphic, you can see, kind of an incremental disk and a absolute disk. All right. Now, in the case of an incremental disk, as we've talked about, you're getting basically, for all intents and purposes, light either passing through or not passing through, but all the areas there around the peripheral of the disk are all basically the same. So you can't really tell where you're at based on the light that's shining through the slots there. Now, in the case of a absolute disk, whenever there is a pattern shining through onto the disk, or onto the photodetector, you're going to get a unique pattern. Okay, and if you get a unique pattern, regardless of the positioning of the shaft, then you know precisely what the position of that shaft is. So that's really what absolute encoders are all about, and that is having a totally unique pattern that is detected, whether we're talking optical or whether we're talking magnetic, because there's a lot of magnetic absolute encoders as well, but having a unique pattern so that that exact location of that shaft or exact position of that shaft can be detected regardless of where it's at. Okay, and there are single turn and multi-turn encoders available too. So multi-turn encoders can be great for those linear applications we've been talking about, where we move up and down, from one end to the other. A multi-turn encoder in that case is probably what you're looking for. Whereas for a rotary type application, a single turn encoder, absolute encoder could be what you're looking for. Okay, so that's kind of a basic difference in terms of, the guts of, if you will, an absolute encoder versus an incremental encoder. Now let's talk about the interface. So, back early in my career, I'm aging myself again. For absolute encoders and resolvers and those sorts of things, you had a lot of really specialized digital type signals. So you would literally have, 16 digital signals that were kind of interpreted, maybe in gray code or maybe in straight binary or maybe binary coded decimal. You'd have 16 electrical signals passing from an absolute encoder or resolver over into a PLC type device. Well, this is 2020. We don't have to do that these days. Now we have a variety of serial interfaces that are available and field buses, which are terrific for this sort of thing, especially CANopen. A lot of you may not be that familiar with CANopen. It is a field bus protocol that we support at Horner very well. Also, it is a very popular field bus protocol from Europe. And there are a lot of manufacturers, including our friends at Encoder Products here in the US, which manufacture encoders that also support CANopen in their offering. So the beauty with CANopen as a network, as a field bus network as it relates to encoders, is CANopen has this really cool synchronous mode. So you can have multiple encoders on a CANopen network, let's say for representing multiple axes of a machine or something, and when a sync signal goes out over the network, and in this case the OCS would be the master of the network, when that sync signal is sent out by the OCS, all the encoders are capturing their exact position at the time they receive the sync signal, and then they're broadcasting that information back to the OCS. And the fact that the OCS doesn't get it all simultaneously on the return isn't that big a deal because all the positions were captured simultaneously with that sync pulse. And the speed can be really pretty fast. You can be talking a few milliseconds here in terms of getting this information back. So CANopen's a great option for absolute encoders. There's other options as well, but that's one I wanted to specifically mention because we've got pretty good experience with that. And just briefly, as kind of a matter of interest, I'll show you a example program here in Cscape. Let me go ahead and close out of the configuration that we just did for that XL series encoder. I'm going to go ahead and open up an application here that's based around the integration of a Encoder Products CANopen encoder. Now, we've interfaced with encoders over CANopen from people like Turk and others, lots of great manufacturers out there. So you're not looking at just one or two choices. But to give you an idea of what we're looking at here, this is really a program that was developed as an example to hand over to a customer to give them a head start on, having all the diagnostic information they could possibly need when it comes to their encoder. So what you see here looks like a fairly busy screen, but it's really been designed as a screen that provides all kinds of diagnostics, kind of pre-drawn, if you will. So anybody who's utilizing CanOpen can just start from that point and take advantage of all this kind of pre-configured data, if you will. So anyway, this is just a example application we have that's available for anybody who wants to integrate an absolute encoder over CanOpen. It's going to be very, very similar whether we're talking about, again, Encoder products or Turk or whoever else we might be talking about from the manufacturer standpoint. But in terms of the configuration, a lion's share of the configuration here from a CanOpen standpoint isn't done in the I/O configuration. It's done in the actual CanOpen networking configuration. So I'm not going to go to the local I/O tab for this configuration. I'm going to go here under CanOpen on my CanOpen network, and I'm going to get a pop-up box here, which is going to give me the ability to configure the encoder. And there's a lot of parameters. It looks a little bit intimidating. It's actually not nearly as intimidating as it looks. For all intents and purposes, we've got this encoder. There's one encoder connected as an example, and it's broadcasting its data both asynchronously and synchronously as an example, back to this OCS, and the data is showing up in a high-speed fashion in one of the %R registers in this case, in one of the general purpose R registers. Okay, so it's kind of beyond the scope of this particular session to go through all the details there, but that should give you a flavor for how that can work. Okay, now the next thing, we're almost done here. One more product I want to show that's a great option when it comes to encoders, and that is one of our newest, well, it is our newest RCC product. So really more accurately, this is a RCC high-speed counter coprocessor block. It looks a lot like one of our smart block I/O blocks. You can see from looking at it there, it's got a couple of terminal strips with 28 I/O points built in, including 12 high-speed inputs, and support for 4 encoders. Okay, so this is a product that goes beyond the 2 encoder limit. Of course, if you need a lot of encoders, CanOpen's another great option as well. We've had applications with customers using as many as 6 encoders on CanOpen, and that seemed to work really well. But there's some things in the RCC 6512 that make it pretty unique. The fact that it supports CAN as well as Ethernet built in, as well as serial. The fact that it does have some local logic capability. It has some real analog filtering available. You can support both 5 volt and 24 volt signal levels on the input side. It supports plus or minus 10 volt analog outputs. So it's a powerhouse when it comes to high-speed counting, and it's really a coprocessor. It's not necessarily designed to be the only controller in an application. It's designed to do all the high-speed stuff really well with some local logic, and then having an overall XL7 or some other, similar OCS kind of taking care of things there. So that's really what it's designed for. It's a coprocessor. Now I'm going to bring Casey in here, and I believe Casey has an actual RCC 6512 that he's going to hold up to his webcam just to give you an idea. There you go.
Let's try to center in here.
Yep. So that's what it looks like. You can get a good idea of size from that. It's hard to show size when you're just looking at a slide or a graphic. So that's a really fantastic product. Really powerful. So.
Absolutely.
All right. Terrific. Okay, so that is our topic for today. Anything you want to add, Casey, in terms of what we've covered, or maybe what I forgot?
Not in particular. It doesn't look like we had any questions come in today, but I would recommend we have some live stream viewers, but we also have people that watch these after the fact. So if they do come with questions, feel free to add them in comments in the video after the session, and we'll definitely get back to them with any information we can. And another thing would be for any future sessions that there are topics that people are looking for, feel free to comment in the questions here or in the comments after the video as well for any recommendations on future topics we want to go over. It'd be really helpful for us to go over information that people are actually looking for sure, that maybe some are most requested.
Absolutely. A couple of things I'll mention. It wouldn't be a YouTube event at all if people weren't asking for you to subscribe. If you do subscribe, you'll get notifications, of course, of our future events, and we're trying to have these approximately once per week. Another thing is, I highly encourage you to register on our website because we have events beyond just YouTube. Where we try and provide topical information both on our products in terms of existing products and new products. That's by registering on our website. You have the ability to download our free Seascape software that I've been showing in our demonstrations. So you'll need to register for that. And as Casey mentioned in the comment section of this video, in addition to all the other things he's mentioned, including our homepage, there's also a link there for the registration page. So if you have yet to register on the Horner website, please do so. We're not going to bombard you with junk mail. We'll be as responsible as we can. And if you're still not happy, if you think we're a little overzealous, you can always unsubscribe. But we don't think you'll need to do that. We think you'll be happy with the amount of information we give you and that we don't overbug you. One last thing. Tomorrow, which for those of you watching this on replay, tomorrow doesn't mean anything. But the 27th of January at 2 p.m. Eastern, we've got a webinar on practical hands-on MQTT. So that's a IoT protocol that a lot of people have heard about. We've done webinars before talking about MQTT. What is it? How does it work? This one is going to be really focused on kind of the hands-on of setting up a simple MQTT setup using kind of open source type tools that are out there and available for you to try, in addition to our products, which offer a free MQTT license currently. So that's something you'll be able to try out. And we're going to show you that tomorrow, January 27th at 2:00 p.m. And keep an eye out again on our YouTube channel for announcements for next week's video, our next week's live stream. Not sure the topic yet, but we'll be announcing it very shortly. Thanks for joining us.